I appreciate it, Marcus. And Kaylee and Mandy are here to help with those as well. We're all on today. So let's talk about optimizing design with the SOLIDWORKS suite of simulation tools. Specifically, how can you use these today? Maybe some you don't have your hands on yet that you'll want to use to save time and money, because that is the name of the game. My name is Philip Morrow. I am one of the applications experts here at MLC. I do all things SOLIDWORKS, but I spend most of my time in simulation and in the 3D experience products, where we have even more simulation tools we'll take a look at today. I've been here with MLC a little over 9 years, so if this is the first time you're hearing my voice, check out our YouTube channel, call us a little more on tech support. Don't be a stranger, but that's my background. That's what gets me here in front of you today. And it's not different really than the rest of our technical team, than Kaylee, who you might know, than our other AEs. We're all here to do these types of things: products education, run tech support, we teach training class, we do consulting jobs with this stuff. Our role here is to help you guys find the right tools for the job and then be successful with those tools. That's it. So that's what we're doing today. And this is what I've put together to show you on simulation. First, I want to give you a little overview of all the product tool sets that are built right into SOLIDWORKS. They have the same interface and that are very easy to get started on. I'm going to do that first one with a case study from an actual race car team. They have a pretty cool use case of using optimization. There's two forms of optimization I think are just really awesome in the FEA or structural analysis world. And then in the same interface, I want to get into doing some optimization for fluid dynamics. And that could be for, gases and fluids mixing around, or a lot of times it's for thermal studies. So we'll talk about how to use that in the interface, and then I'll take it one level higher. Actually get outside of the SOLIDWORKS interface to some connected tools that come down through 3D experience, but still give us all these benefits of having parametric designs and SOLIDWORKS files. So after each one of these, I will take a little pause. I'll take a look at what's been coming in on the questions panel, how hard you guys have been making Kaylee work to answer those questions. So don't be shy with those. We'll pause along the way, and at the end, we'll summarize as well. But let's dive right in with some of these simulation tools, because the name of the game here in whatever tool set you use is to save time and money, to literally reduce the amount of physical prototyping you're doing and use these sim tools as a design tool, not a reverse engineering or failure diagnostics tool. Sure, they work for that, but how can we make one prototype and get it right the first time? That means avoiding errors, avoiding rework, but also saving on material costs and manpower through optimization. Is it as light as it could be? Did you choose the best material you could? Not just guess and check, but letting the software optimize the design. So you don't just pass, but you do better than your competitors the first time. And I think you guys kind of all understand these concepts as SOLIDWORKS users. When you're working on some engineering design life cycle, the whole point of these types of tools built into SOLIDWORKS is to do more tasks in parallel, right? Use these sim tools as part of your design process. There's no reason to wait until things go all the way down to a finished assembly to even start the simulation. As soon as the file exists, you can do that and things update. And that's what I want to show you with all of these tool sets, that connected nature. So, traditionally we might have all made something completely in the 3D CAD, maybe then did a simulation, maybe then did a physical prototype and tested, and then iterated. I mean, that's how everyone gets started with pretty much any design. Moving from there into the world of even guess and check simulation, inside of SOLIDWORKS, is just going to change this. So we build our virtual prototype. As soon as you've saved the first file, simulate the performance and do some design iterations here before making the prototype. In fact, not just guess and check here. What I'm showing at the bottom for this miter saw is the cover, the guard that goes over the blade. And this guard had resonance frequency problems. It vibrates, has sympathetic resonance depending on how fast the blade is spinning. Where should we add some extra material, some supports to thicken this thing up? Yeah, we can guess and check, but we can ask SOLIDWORKS to tell us the absolute optimal place to put those using the least amount of material, making something that's still manufacturable, and then build our first real-world prototype. So we want to shorten these cycles down. We want to do everything in parallel, and when we come out of the gate, we don't just want to pass, we want to get the best solution that we can. So when we're talking just inside of SOLIDWORKS Simulation, there's really 3 worlds of simulation. There's finite element analysis. You'll hear me call that FEA. That's our structural analysis. Is it strong enough? Does it vibrate too much? What's its fatigue? Is it going to overheat? The second one is fluid dynamics. And yeah, normally you think about airflow, water flow, impellers, but also this is a perfect place for thermal analysis, things like electronics or lighting structures that heat up, anything with convective cooling, of course. And then also there is a plastics injection molding simulation tool inside of SOLIDWORKS as well. It's just called SOLIDWORKS Plastics. This one's a little bit different because it simulates the manufacturing process, the injection molding process. But if you're making any plastic part out there, you ought to have the first level of that package. It's a simple way to know, is the part too thick, too thin? Do we need to have the right draft on walls? Are we going to have a short shot? So by the time we send this out to manufacturing, we don't get A, a high quote back, or B, some changed part because it wasn't manufacturable. It's an obvious design tool when there, all the way up to the higher levels for if you are a mold maker or own an injection mold machine. I'm going to focus today, though, on the ones that aren't from manufacturing. Is it strong enough? Can it survive? Can we optimize it? Designs. So in those packages, there's usually 3 tiers. I just want to cover these up front. There's a standard, professional, and premium tier. Just like there is for SOLIDWORKS CAD, you can buy additional licensing for simulation. Now, I do want to point out, if you buy SOLIDWORKS Premium, which is just SOLIDWORKS CAD Premium, they throw in the linear static solver you see kind of on the top left side of the screen. So you can do FEA on parts and assemblies in SOLIDWORKS Premium. But if you buy a full simulation license, it has the word simulation in the license, then you can buy Standard, Pro, and Professional. The Standard throws in fatigue and motion above SOLIDWORKS Premium. And I mean, the most common package for like 90% of users is the Professional package. It's got everything in Standard. Plus, once you've done your work in setting up a static sim, you might as well do frequency analysis, buckling analysis. There's a drop test in there. And I'm going to show you guys 2 different types of optimization studies in there to get to that cutting edge. On the higher level, the premium side, these can be a little bit niche. I like to talk to folks and make sure they really need it when they get it. A lot of folks do, because if you're in non-linear worlds, something maybe a gasketing application or a material that doesn't act linearly, or you're doing composites like fiberglass and carbon fiber, or you need dynamics for earthquakes or motors that are running and you need more feedback than just natural resonance frequency, that's going to take you there. And then a little later on, I might show you even the next level above that in case that wasn't enough power. On the flow side, there's really just one big license. There's SOLIDWORKS Flow Simulation. It does everything you need. It is the most powerful tool for simulation that is built inside SOLIDWORKS that we know and love. It's awesome. It's actually one of the easier sim tools to use, just like SOLIDWORKS Plastics, but it's solving some of the most complicated stuff. And of course, it puts out the coolest visuals. Now, this one package will do everything, but I want to mention there's 2 add-ons that you could do to extend its functionality. There's an electronics cooling module, particularly if you're doing a lot of electronics. You want to heat up a resistor, send a current through something and see it get hot. You're working with maybe 2 resistor component models. You want to extend the fan curve database, heat pipes. There's extra equations for this stuff. The other extension is specific to HVAC or people working with advanced radiation models fit there. If you're doing something in the aerospace industry, radiation can be very important there. If you want to take into account the spectrum of light, the color of light, you're doing some kind of lighting arrangement, or send radiation through semi-transparent materials. So those 2 sections. But for 90% of people, SOLIDWORKS Flow Simulation is where it's at. And then SOLIDWORKS Plastics, if you're making any plastic part at all. The way I think about these is pretty simple. Do you make something made out of plastics? Yes, you need Plastic Standard. Easy tool to use. It will help you make a nice manufacturable part right out of the gate. Do you own the actual injection molder? Look at Plastics Professional. You can do runner balancing, multi-cavital modes, get really accurate cooling time, really do your cycle times accurately, and even do overmolding there. And then, are you a mold maker that's actually worried about warpage after the mold opens? You want to run cooling lines. Then you might go all the way to Plastics Premium. So I know that's a fast overview, but those are the main areas of the software for simulation that are inside of the SOLIDWORKS CAD interface you guys already know. I think, better than explaining them here, I want to get hands-on and show them to you. So for FEA, for finite element analysis, for structural analysis, I mentioned GIAFFONE Racing, this race car company. And they have a part that is failing that is similar to really what a lot of racing teams find when you're in a stock car situation. I don't mean like NASCAR stock car. I mean you buy a car that's out there somewhere, a Focus ST for rally racing, whatever, and then you just start modifying, you start pushing the limits. And this is a component that attaches the actual steering mechanism to the wheel. And sometimes they fail quickly. Actually, in little kids like soapbox derbies, you'll see this part fail immediately. What they actually found here is this component was failing during a racing series. They would do 20, 25 races in their whole season of racing. And after 15 or so, this part would fail. And I've seen how it rips apart. And they thought, okay, well, this is a cast component that comes with a car. It's pretty heavy. We're making all sorts of things out of aluminum that's easy for us to machine. We know that aluminum generally has better fatigue lifespan, but it's not as strong, right? It's going to flex more. It's going to have problems probably. Can we just swap this out with aluminum? And because we have SOLIDWORKS Simulation, it's like, well, let's find out the answer to that question and let's take this further and then optimize it if it survives. So that's the process I want to take you through. I'm going to show you how to set up a simulation like this, how to learn some stuff and say, well, will it survive? What do we learn just from those results? How to optimize this thing based on how we can manufacture it. In this case, these guys have a machine shop. And then even how to go further with topology optimization and let SOLIDWORKS come up with an optimized shape that may be, a little bit more organic. So step number one is this model setup. And I'm just going to keep in mind a couple of goals here. I need to be able to survive a certain loading. This is kind of the weight of the car taking a hard turn, 6,000 newtons. You could also keep this in your mind as like a factor of safety. Factor of safety's got to be above, say, 1.5. So I have a goal for strength, and then I have a goal for deflection. We figure if this thing starts deflecting, more than 0.1 millimeters, maybe the handling is no good anymore in the steering, and that's going to be called a failure for us as well. So let's switch over to SOLIDWORKS, where I have an assembly of the steering assembly, a suspension assembly, and I want to get down to working on these parts. Now, the cool thing about SOLIDWORKS in the interface or anything connected to it is you don't need to save your parts out to the side and do something different for FEA. You can set up the sim right here inside the same assembly. All I'm going to use for this is a configuration where I suppress most of the components I'm not interested in, so I simplify down. That's about it. Now I've got the full suite of simulation added in. If you're in SOLIDWORKS Premium or if you get into simulation, go under Tools and Add-ins. All you got to do is check on SOLIDWORKS Simulation. As long as you have a file open, that's going to give you the simulation tab up on the command manager so you get all the simulation tools. And just so you know, it gives you the simulation tutorials just under the help drop-down menu and a crazy simulation drop-down menu from the top over here with all sorts of settings for it. So there's a lot of self-help stuff to get started, but watch how I do this. I think just right-clicking and working with a tree, the way you already know how to use SOLIDWORKS, you'll know how to use the simulation tools. So I'm just going to go up here to the top left and hit New Study. Now, I'm lucky enough to have the SOLIDWORKS Premium license, or SOLIDWORKS Simulation Premium license, but even if you have the lowest level of sim licensing, you'll have static studies available. Right? And if you're even going to do a higher level type of simulation, you'll probably start with a static. So I'm just going to say static, hit the green check, and SOLIDWORKS gives me a simulation tree. Now I've got my CAD tree up top, and I've got my simulation tree down below. And before I even get into the simulation tree, I think what I'm going to do is set myself up some sensors for those goals I was talking about. Check out in the top of my tree, there is a folder up here that says sensors. It's one of the many folders that could be showing at any time in your tree. And I can add a sensor here that monitors simulation data. You could really do this for, is my assembly getting too heavy? Are parts too far apart? But I'm gonna say, let's watch stress, or we could watch our displacement. Let's watch displacement, total displacement here in millimeters. And I wanna be alerted if the value is ever greater than 0.1 millimeters. Boom, it shows up like a rebuild warning. Now I can do whatever I want in sim, whatever in my assembly. This is kind of like, the check engine light in my car. If this thing blows up and turns red, I'll know, oh, I've gone too far past my goals. Cool, so I've got some sensors up top. Keep in my mind. Now let's get down on the bottom half of the tree where I'm working with simulation. And I'm just gonna work top to bottom like you do in a regular CAD tree. First, I've got some parts that show the different bodies that are in here. And a couple of these already knew what material to be. They're a cast carbon steel. This one didn't. That's okay. I'll right click it and apply a material to it. Cool thing about applying materials when you're in a simulation, the necessary material properties are color coded. So if you're wondering, oh, what materials do I really need for this type of simulation, you can see, which ones are red here in the list. All right, I'm gonna apply that. I've got a plain carbon steel and a cast carbon steel for a couple other ones. Got green checks there, that looks good. I'm gonna let the default connections that SOLIDWORKS comes up with for these different bodies work for me. And then I just need to get into the loading and the fixturing of the real world. By fixturing, I mean all that stuff I suppressed. So one easy fixture here would be to apply a roller slider on this back face. Basically, this face is bolted on a material that I've suppressed, so it can't move in that direction. There would be material here holding it and saying, you can't move in the X direction. The other thing is that it's actually bolted to those materials. And yeah, I could go do a bolt connector. There's actually all sorts of connectors, bolts, springs, edge wells, links, but I'm gonna keep things simple, man. I'm just gonna go fixed hinge and give this kind of a hinging behavior as if there were bolts inside of these three holes. Okay, simple enough. I've defined how we're attached to the rest of the world that I've gotten rid of. If I keep moving down the tree here, I need to add the loading. And this force happens right on this ball here, this ball joint where the steering column actually connects to it with a linkage rod. And it happens in a specific direction. So I'm gonna set up a direction here relative to, oh, my front plane looks pretty good. We're gonna run a 6,000 Newton load. And I could see with these fuchsia colored arrows on the screen, how hard is that to know what direction the load is going? Those are my engineering assumptions, my engineering inputs. That's actually all you need. Materials on your parts, fixtures, and loads. SOLIDWORKS is going to take care of how they're connected together. And by default, it's going to use its own meshing. If you want to know a lot about meshing, please come to my training class. There is a lot to talk about with meshing. But if you don't know a lot about it, that's okay. You're going to get in a pretty good ballpark here. And look, it only takes a couple seconds to run, and it uses its default settings. So how hard was that setup there? I used a couple of sensors to let me know, well, if I fail, I can go check those out. I applied the real world conditions to it, ran it with some defaults. The only inputs I really gave it were materials, fixtures, and loads. So what did I learn from that? Am I meeting the goals? Is my part passing? What can we learn? Well, I got results, so we can find out. And I'll show you exactly how I look at results. One thing is I can go ahead and hide these different arrows. I don't really need to see all the green and purple, so I'll clean that up. And the first thing I'm looking at is a displacement plot. It's an exaggerated displacement plot. So it's exaggerated the amount of displacement 180 times over on my screen. They'll tell me that because it probably only moved a small amount. And maybe I wouldn't even be able to see that with my human eye. Really, the highest number that you see over here on the top of the color legend is the max that it's calculated. So 0.04 millimeters is what it calculated. Well, that survives the deflection goal, and I can tell because my sensors are not red or yellow. I didn't get any check warning lights there, so I knew that that survived. And we know that the cast one does survive. Displacement is the #1 thing this software outputs. So if you don't mess with the mesh, if you don't know all the rules of the game, you probably still have decent displacement numbers. And what I'm really looking at here is if I right-click my displacement plot and animate it, does the direction of the displacements and the place where I see the maximum most red, does that make sense? In this case, yeah, red's not bad. It's a very small number, but that's where the most is. That's where I'd expect it to be. Those are the directions I probably set things up correctly. Okay, then next question would be, does it survive? And that's normally where I get to stress and factor safety. These were already plotted for me. And I can actually tell from this plot here that it did survive. If it failed, it would show me with a red arrow. Factor of safety will show me that. But I like to see where is the max stress on here. In fact, I'm going to add a flag to it so it just shows me here's your max stress. It's right there. Now, I've seen the part in the real world where it fails after a lot of fatigue of turning left and right, and this is where the failure point is. So luckily for me, I have a real world sanity check there. And if I wanted to see if it really survived this loading, I can see this is less than 150 megapascals. That was my goal. about 138, so that's good. And I could also check out the factor of safety plot. Really the lowest value on the factor of safety plot is important to me. It's about 1.6, so it survives this amount of loading with 60% less than the material's capability. So yeah, we're all good. We learned quite a bit there. Okay, so we found we survived. How about if we just switch this thing to aluminum? Will that survive? Guys, if you do something a second time inside of SOLIDWORKS, you should call us. There's a way to do it once, and so of course there is here, even if you're in different files. But what I'm going to do is just copy this study, static 3, I'm going to call it static 4. So I get a duplicate. Bang, there we go. I've got a new study tab here. It looks exactly like the old one. I'm just going to go to my parts folder and apply a different material. In this case, I'm going to use an aluminum that I'm familiar with. I'm going to go with a 6061 T6. Ought to be a fairly strong aluminum. And I can just run this again. I'm not worried about, the fixtures and the loading, the setup. I verified my displacements were where I wanted it. I just want to know about this other material. And right away, I can see that I've got some type of rebuild warning here in the sensors. All right, something's no good. And it looks like my stress is okay. My stress didn't go up by that much at all. But my displacement went over. I'm like 0.13 millimeters. So we might already call this a failure. I guess, let's say we put the driver in the car. We put him on the track with our aluminum thing because we know it's not going to kill him. It's not going to break. And he goes, you know what? The steering handling, it's okay. You can live with 0.13. I'll go, great. Well, if this is successful, what else could I learn here? What else could I use to optimize my part? And I'm going to show you how to do this without even having to get into the simulation professional license. Let's say you're still in SOLIDWORKS Premium, right? I haven't got anything out of that licensing yet. When I right-click my plots, I can do section views, and there's a really cool one here called ISO clipping. And ISO clipping allows me to move a slider and visualize where the stress is in a material. So for instance, at the high end of the slider, I can see, okay, this is the material here that is holding a whole lot of stress for this type of loading. And if I go towards the other end, I see, wow, when I have the slider down here, there's a section down here which is basically doing nothing in its contribution to supporting this load. It's super low stress. This tells me right away I could probably remove some material here and not have a big effect on the results for this specific loading. In fact, I'm going to jump back to the model tab. If you're using one of the last 3 or 4 releases of SOLIDWORKS and a good graphics card, you can use this simulation display functionality to show your simulation results in the regular modeling environment. It's just another super cool thing about being inside the same SOLIDWORKS environment. So check it out now. I am in the regular modeling tree. I'm not in the simulation tree, and I could still see my results right here. Maybe you want to 3D print this with a color 3D printer or photo render it out and send it to somebody. That's pretty sweet. I'm going to use this like a template, right? I got kind of like a 3D picture of my results here. I'm just going to start up a new sketch right on top of here. I am doing this in context of the assembly. Let me know, hey, you're drawing a sketch at the assembly level. Are you sure you want to do that? And I'm thinking, yeah, I'm going to do that. Fine by me. Let's go ahead and put this sketch in. Now, I'm a pretty big stickler for CAD modeling stuff inside of here, so I think I am going to actually throw a dimension on here. I don't know what number is going to work out real good, but I'm using this as if it was matching up the template underneath. And it looks like I could add a tangent relationship, and cool, I got a fully defined sketch. I hope you all do that when you're sketching. Fully defined every time. If you don't know that saying, type it into YouTube right now. Check out fully define every time. All right, I'm going to add in a little assembly feature here then to cut that material away. Cool thing about doing this at the assembly level is it only has to happen here. You don't have to push that down to the part. So I can just do a what if of that part cut here in the assembly. I'm going to jump back over to my simulation now and just rerun it and find out, well, I took out a lot of material. I shaved a bunch of weight right there. Am I in trouble now? Is this now going to fail one of my sensors? This thing runs pretty fast, of course, and it looks like to me the displacement is basically unchanged, 0.13 millimeters. Stress is still passing, also basically unchanged, because I know that that material was doing almost nothing to support the loading, and now I've shaved some weight. That's just in SOLIDWORKS Premium or Simulation Standard. Nothing more advanced about that. In fact, I wouldn't even call that optimization. That's more the guess and check. Yeah, I can do things digitally, so I'm better than just trying it out in the real world and iterating, but I'm not yet to optimizing. So these tools let you try stuff side by side, really compare features. In fact, there's a lovely compare feature tool here where you can look at your results side by side on the same screen. Even if you're in different files, you can import study features between those files. So you don't have to sit in one assembly. You can jump over to another part and pull this simulation right over and eliminate that read work and just make better designs altogether. So why don't we let SOLIDWORKS optimize this thing a little bit? Let's see what we can do. Well, to do this, you do need the Simulation Professional licensing. So now I'm getting up to Sim Pro. And what I'm going to insert is called a design study. I'm just going to add a new design study. What a design study allows me to do is pick variables, things to change inside of here, constraints like my sensors, you know, this thing, factor of safety can't get too low, and then a goal, which is commonly minimize mass. So a couple that I'm going to keep in mind here is I'm going to change the thickness of this part. I'm going to let that go down as low as 3.5. It can get thinner, let's say, until we get that stress. And there's a radius that controls a fillet that we get smaller as well. But I can't let that stress get over 150 megapascals. That's the same thing as saying I can't let my factor of safety get too low. So I've got a couple of variables made here already. I want to show you, you can make these at any point, these parameters, while you're using SOLIDWORKS. It's kind of like making equations. Anywhere that you've got a number out in the software, you can link in as a parameter. So I'm just going to take my overall thickness, tell SOLIDWORKS to range this from, well, I better remember my numbers, 3.5 to 5. I'll get a smaller. I want to take a radius, and I'm not even giving it a range, a step size or discrete values to try, which I could. I'm going to let SOLIDWORKS actually determine what size in between 8 millimeters and 12 millimeters is going to be acceptable. Now for my constraint, I'm going to use that sensor. It's already available to me and say, hey, my stress 1 must be less than 150 megapascals in my static 4 simulation, the last one we ran. And then for the goals, well, I am going to add a sensor for my goals, just like I did before. This time, all I'm doing is adding a sensor to monitor the mass properties. And my goal is to minimize the mass. All right, if you've thought about all these windows appropriately ahead of time, you can just hit the run button. It's right here next to optimize. And depending on the number of variables you've included in this study, which there's no limit to, SOLIDWORKS will come up with a number of scenarios to run. In my case, it's running 11 scenarios. And what I want you to notice is that it's actually changing the geometry out in the graphics area. So when it tries, say, a minimum thickness or a maximum thickness, you'll see the CAD part change back there. You might want to use configurations for this if you're doing some what-if studies. And then it'll split the difference. It'll go, okay, how close did we get to our goals? Can we make it even thicker, thinner? Let's go that direction. So we're seeing each iteration stack up here. Now, what I'm expecting is as we get a few iterations in, of course, every iteration is a completely new run of my simulation. So sometimes you don't get to see this many sims run live in a meeting, but we're running 11 of them right here. And I'm expecting a few of them are going to start to fail. We'll probably get outside the window. Otherwise, we'll end up on just the minimum values, and it'll say, hey, you can go as small as you typed in, you'll still pass. But there's a good example. Iteration 4, it tried the very smallest thickness and also the smallest radius, 3.5 for the thickness, 8 millimeters for the radius, and that got just over 150 megapascals. So it color-coded that in red, showed the iteration that was failing. This is kind of nice because I chose it to range through values. I didn't say, let's go with discrete values, like I only have these available, range. I might look at these though and say, you know what, it's a lot easier for me to manufacture one than the other. You know, I can buy, you know, plate steel at some thickness. I don't have to go machine afterwards. That one's pretty close. I'm going to go there. So when this is done, you can just choose the column header that you want to end up on. For me, I want to end up on the optimal one. I want to make it as good as it can be. All right, we're processing our 11th scenario here. We've really only failed for 2. And what I'm going to end up here is a part that now should survive, hopefully, our series in fatigue. and is made lighter, as light as it can be, keeping in mind the manufacturing processes that are available to me, right? Like I can throw this on a CNC, maybe I've got a mill and I'm going to be machining aluminum. There's really no downside for me there. I can end up with a thickness of 4.25, a radius of 8 millimeters, and I'm going to shave a few grams of weight off of this thing. I'm still going to survive by quite a lot. So I can get almost down to my minimums, and here is the part in its final shape. So if you can think about those variables and goals, you might as well optimize. Let's put our first one out there close to the limit. Like, not just is it going to survive, but how good could it be? Let's maximize the performance. Now, of course, there's another way to do this that I want to talk about. I mean, just the material change alone, just getting the simulation, saved us 30%, saved us quite a bit on the mass. Additionally, we cut 30% after that through this optimization. But there's another method we could use, which is in Simulation Professional. This is something that came in 3 or 4 years ago, and it's really a benefit of the technology share that SOLIDWORKS Simulation has with Dassault Systems, who owns Abaqus and the Simulia brand and all that. And it's called topology optimization. In this one, I'm not going to tell SOLIDWORKS where I want to remove material and what dimensions I want to exactly control. No, I'm going to give SOLIDWORKS a part that has extra material on it. It's kind of bulked up. And then I'm going to give it the same type of simulation setup, a few differences. And I'm going to ask SOLIDWORKS to figure out where can it remove material. What it'll do is iteratively pull little parts out of the mesh and run the simulation and figure out, oh, did this get better or worse? And then try different areas. So this is going to run quite a bit longer than the last studies. If the last ones took 20 seconds, this one's going to take 20 minutes. So keep that in mind. But you end up with really interesting ergonomic shapes that end up looking a lot like things you see in nature, because nature is very good at supporting, the loading of like a plant or a tree for exactly what that thing encounters. But sometimes it's not as easy to manufacture. So I'm going to show you some ways to get around that as well. So let's open up another file here, because I mentioned you should really start with something overbulked. Now this has to be a single part file or a single body to do this with, and go ahead and give it way more material than it needs. So imagine this is my same steering bracket. Well, it just looks like a big C shape basically, right? What I've done is I've split lined out the footprint of that steering bracket so you can still see it here, and I've got the 3 bolt holes in place. So that's like how much extra material I put on this thing. And then because we couldn't have an assembly here, I haven't put in the ball joint that was in between these, but I'm going to deal with that as well. Let's take a look at my topology study tree, right? It's the same interface as SOLIDWORKS. It's still a tree. Just move from top to bottom and right-click stuff. You guys are going to know how to use it. And what I've got here is, in place of those bolts, this same fixed hinge fixture. So keeping it simple and just putting fixed hinges for the bolts. But in place of the loading, I've used a remote mass. With a remote mass or remote load, you don't have to mesh something. You can just say, hey, here's where the center of mass of that thing is. Here's how much it weighs, and here's what it connects to. And that's what I'm doing here with the loading. Here's a point in space where the loading is concentrated, but really it connects over to these 2 spots. Now, what's new in this tree is the next section, the goals and constraints section and material controls. If I take a look here at goals and constraints, what you're going to see is a best stiffness to weight ratio is the goal the software is going for. And that's the most normal and common type of goal to have on here. You can actually add to it those other goals that I had as sensors too, though. So we can say it can't displace over a certain amount, or its stress can't get too high, or in this case, its frequency. We could say it couldn't have too low of a natural resonance frequency. So we're saying that we have a mass constraint. We're hoping to reduce this entire body by 90%, but we want to maintain a good stiffness to weight ratio. The other thing that's new here is the manufacturing controls. What we've got is preserved regions around where the bushings would be for my actual steering knuckle and around my bolts, because I don't want SOLIDWORKS to remove any piece of material or I'd get bolt tear out. You can also specify a thickness control so it doesn't get too thin, a demold direction if this is cast or an injection molded, or sometimes that's nice just in the direction a machine head would come at it if it's in a CNC, and symmetry as well. You don't have to cut things in half. You can just apply symmetry and it'll solve in half the time. So what does this output when it's done solving here. Actually, let's solve this one at a time. It takes a little time. Well, you get two things out of it. One, you can directly get a finished part. You can save that out as a new configuration or as a new part file. So I've run this in the past and I've just saved out to new configuration. This part, it is a solid body, a piece of mesh geometry, but it's solid. We can weigh it. This is called a smoothed mesh body, but as you can tell, it's kind of bumpy. This is the shape that SOLIDWORKS came up with on its own out of that C shape. You can see a bunch of material missing there in the beginning, in the middle. It's actually lighter than my original shape, my original part, but it's hard to manufacture. I could cast it, I could 3D print it, but it's going to take some work. So instead, if you are stuck, not with just being able to 3D print or cast in your application, I would say the other output it puts out is a material mass plot and stress plots, just like you saw earlier, which you can show in the regular modeling environment and use like a template the same way I use to cut my material out of the last part. If you do something like that and you really apply yourself and you get into SOLIDWORKS surfacing or X shape, maybe you come up with something that looks like this. Maybe still not the easiest in the world to manufacture, but looks a lot smoother. And we got these ideas from the results of that topology study. So this is the workflows I'm talking about. Start with something that's really overly bulked, get your topology result, and just display that result on top of your overbulked model and start carving away at it like it's clay to come up something that you can manufacture. Or skip that step, get your result, 3D print it, cast it. Right, here's another example of that for a lifting mechanism on the hood of an RV. It's a very heavy hood, and we wanted to shave some weight here. An overbulked model to begin with. When the results came out, that's what you see here in the middle. These results displayed on top of the regular overbulked piece of geometry. And just looking at that and sketching and tracing around, coming up with a third picture here that is a shape that I would not have guessed and made up on my own. You know, this kind of webbing structures in the middle of it, but it's extremely light in comparison to, its actual use case, where it's getting plugged in. To support the opening load, it's kind of perfectly designed for that. And all of this can be done just inside of SOLIDWORKS Simulation Professional. So that's an example of the FEA optimization process, from how simple it is to set stuff up, even if you have SOLIDWORKS Premium, and what you can learn from that stuff. Going into optimization, parametric, which has been around for years, or the fancy topology, which has been in there for 3 or 4 years now. And that's actually what GIAFFONE Racing ended up using on a second component when they came up for this. The first one, the steering knuckle, was pretty cool. The next one they actually did end up casting. They took the results straight out of topology optimization. And they were able to do this by adding Simulation Professional. They also added SOLIDWORKS PDM for their data management solution. And they ended up cutting 2 months from their development cycle, reducing their upright weight by 60%. The upright's the name of that suspension component, and ultimately entered their rally racing with something that they knew would work better, looks cooler, is stronger and lighter in methods that they're able to manufacture. So I think they're a great use case, and that's how I see these tools being used by everyday engineers, not just the ones that are off there and solving on some cloud computers for months and months to try a million design iterations, but really tools that you can use for where the rubber meets the road. If I can use a race car pun. Actually, there's a great question here I could go ahead and field. This one came in about the meshing. Within the FEA software, can you modify the meshes, and what parameters can you customize? The answer is yes. There's quite a few that you can customize. Let me close a few files and get back to the one where I didn't really show meshing here because I just used the built-in one for the software. This SOLIDWORKS, you can use a tetrahedral solid mesh, a couple different forms of it, a shell mesh, or beam element meshing. When you're creating a mesh, there's a couple of different algorithms for the mesh as well. I'm a big fan of the blended curvature if you're in the latest versions of the software, 2022. And you can also do these locally through applying mesh controls, so you can just refine the mesh where you need it. If you're interested in that stuff, we spend a third of my training class on that because it is really how you understand that you can trust your results and get efficient solve times, so let us know. And then a little later, when I show maybe next level software that connects to SOLIDWORKS, I'll show you a few more capabilities for meshing if somehow that wasn't enough. All right, excellent question. Keep them coming. This, using SOLIDWORKS, sometimes it's like, it makes it so easy to do things. It's like looking at the tip of the iceberg. But of course, if you're in the world of simulation, there's a whole iceberg down there of functionality and questions that you can dig into. And SOLIDWORKS really does have all those deeper things. They've just been excellent at picking the presets that work 95% of the time, so you don't have to become some wizard of FEA to do these things. The same is true of CFD, of computational fluid dynamics. The software that impresses me the most, I think, out of SOLIDWORKS, because it does quite a lot of things. And its place is really best as the same as I said for FEA. Use this as your design tool. This is a general purpose flow and heat transfer tool. You really can't disconnect those two things, and it's fully integrated in the SOLIDWORKS interface, just like SOLIDWORKS Simulation, so you can make use of configurations, do what-if studies, optimize stuff, right? Simulate the things as you're designing them before they get out the door, especially in a world where fluids a lot of times are counterintuitive, or not as obvious where the max stress or max displacement should be. Now, this software, doesn't matter if you're running internal flows or external flows or both. It can deal with incompressible and compressible fluids, even if it's non-Newtonian fluid like blood or some kind of oil and gas, slurry for frac pumping or whatever it might be. You really don't need to specify whether you're dealing with laminar or turbulence either. While you have controls over these, it takes care of all that for you and where things are transitioning. And then you can't really turn off the heat transfer solution inside of this. Most people think of convection first when you go here. It is technically a more accurate place to do all of your heat transfer. And even in a gas like air, as things heat, they get less dense, they rise, so heat transfer is always happening. And then because it's a tool, like all of our SOLIDWORKS tools here, all of them that I will show you, they're connected together. So let's say we figure out how hot something gets or how much pressure is on something, a billboard in a hurricane, force wind. This is coupled with the SOLIDWORKS simulation tools you've just seen. So based on that temperature profile, that pressure distribution, does our thing survive? How far does it bend? How much stress is in it? We can determine all of that as well. There's a few capabilities that have come in the last handful of years that have really, really impressed me. I've been using the software for about 7 years, and every year, like the rest of SOLIDWORKS, it just gets more powerful. Of course, we can do parametric optimization here, like you've seen for Sim. So we can say within this window, how long does our pipe need to be to get this pressure drop, whatever our goal is. We can do those as what-if studies or design of experiment studies. That's a new expansion. This has solution adaptive meshing, and I want to mention, since I got the question, so does our regular simulation tool. So we can actually, during the solve, pause and have the software refine the mesh in areas where you have, say, high rates of change or high gradients. It can do that automatically instead of locally controlling them only. If you're dealing with rotating geometries like impellers, we have a sliding mesh functionality to actually spin them, and a free surface functionality so we can see the interface between things that don't mix, like air and water or oil and water, this kind of stuff. Even predict decibel output if you're making mufflers or compressors or something like that. So for me, it's been the most fun because it just fits so many applications. It's wild. In Central Texas, where I am, we do a lot of thermal stuff for electronics. In South Texas, it's a lot of the oil and gas industry. So in North Texas, we get into a lot of medical devices, and really this thing just gets used across the board and puts out probably the coolest outputs. I'm always going first to the hard numbers. Let's see if we survived. But when we were explaining why we're making a design change, what was counterintuitive about a flow, the visuals here are something that everybody can understand, and most marketing teams want to get their hands on. It's really not just for airflow and for drones. Originally, this was made for rocket nozzle design, but that was 20 or so years ago. Actually, it was more. That was in the late 80s when the first code was written, so it has evolved quite a bit. But the two main reasons I tell folks to come into CFD, one is that things are not intuitive with flow, like I've mentioned, right? If you're driving on the highway in your pickup truck, I got a Ford Ranger here, am I going to get better gas mileage with the tailgate up or down? Some guys are thinking about it right now, right? I always think, you know, less resistance, less drag, so down's got to be good. It's actually the other way around. It's actually up. Mythbusters did this on the show and did it in a wind tunnel to prove it as well. When you get the tailgate up, you get kind of a vortexing body of air. They call it a virtual body that exists in the bed, and it just allows the rest of the air to slip over some air that's not moving. It's almost like your truck turns into the shape of like an oval, and you don't get that buffeting air over the tailgate. So counterintuitive stuff. The other reason is thermals. It's a more accurate place to do the thermals. There are some actual reasons in the math for this to be the case. And a lot of it is because you don't have to enter something like a convection coefficient. The software makes this a distribution everywhere and figures it all out for you. It's also a little easier on meshing if you are dealing with things like little resistor legs and things that would be more complicated to mesh in FEA. It does have a little bit of a longer solve time. To be, you know, expected out of CFD. It's not crazy. And a cool thing is you get real-time results while it's solving. So you actually don't even have to wait till it's finished to see your results. You get to see it while it happens. So that's pretty great. So the one I want to show you today, the setup is about exhaust mixing. You might see this a lot in exhausts on diesels nowadays. It's really important that we mix urea evenly into the exhaust. This is a similar type of situation. We want to make sure when our exhaust gets down the pipe that it's very evenly mixed, whether it's entering a catalytic converter we don't want to wear out, or it's something like a urea application. And I'm gonna do some what if here, and then I'll talk a little bit of optimization. So this is my overall setup. I've got inlet on one side, the left side here into gray, where I've got some exhaust gas coming in. It's hot, and I know a mass flow rate being produced. On the other side, I'm mixing in some air, just pulling in air at 40 degrees C, so cooler than it is in the summer in Texas, and a mass flow rate. And I want to get really sufficient mixing and, you know, low temperature at the other end, especially in this case if we were feeding back into an engine, something like going through a PCV valve, something like that. So in this software, we use a wizard to set things up. In fact, I'm going to get this open and show you what it looks like in the software itself. So I know you guys want to see it handled over there. This is one of the only softwares where I use a wizard. It's a lot better than that paperclip that used to be in Microsoft Word. The wizard here controls all sorts of things about the solver and the mesher that I don't have to worry about if I just go through the wizard. And I get a nice tree structure as you would in SolidWorks, so I just move top to bottom. So here's what I've entered in my wizard. I'm running an internal flow, so I've capped off the ends of my pipes, and I don't really care in this case about conduction. I'm not running a transient study, so I don't have time dependency on. I could turn on gravity, but things are flowing pretty fast. So this tells the software already it doesn't need to mesh the solid bodies or run conduction equations. I didn't have to like figure that out in some hard solver. I just get in the wizard and check on the stuff that, you know, I want to know about. All right, the fluids that I'm running through it in this case is just air and another fluid that I've called exhaust gases. There is a big material database over here called the engineering database. It houses all my materials, all my fan curves, all my filter medias, really anything I want to stick in the tree. So I've made a material separate from air called the exhaust gas that's going to be getting mixed together. I've got some default wall conditions, meaning it's adiabatic. The only way that heat comes in or out is through the inlets and outlets that I tell it. And then I've got a smooth wall, so zero slip at the wall assumption here. I don't have a rusty pipe, but I could. And then I've got some starting conditions. We're going to start things off at 1 atmosphere of pressure, 40 degrees C, and then those things are going to change, you know, as the simulation runs. The initial concentration is that everything's filled with air and no exhaust gas. Running through the wizard then gives you a tree. Now there's a bunch of stuff that could be in this tree, heat sources, fans, all sorts of stuff. But right now it's just giving me stuff that I said I wanted in the wizard. So it automatically found my computational domain. I didn't have to go, you know, draw some kind of wind tunnel like you do in other softwares. I don't have any subdomains like coolant lines that are separate or anything. So I had to set up boundary conditions. Boundary conditions just set up the problem description. So for instance, on one side here, you can see a little better, I've got inlet mass flow of what I know, 100% exhaust gas. On the other side, 0.05 inlet mass flow, 100% air. And if you forget to change something like what temperature it's at, It's just going to take your temperature from the wizard. That stuff will become the default. So don't worry if you go through those panels and you forget to type something in. It's not going to throw everything off. Now, there are some goals I've made here as well. Goals are what you really want to monitor while it's solving. While this thing solves, it has a bunch of interior goals, inside goals that it's going to figure out. But hey, if you want to know the max temperature somewhere, set it up as a goal. When you're done, you can just ask it and it tells you the number. It already calculated it for you. You don't need to go probe it. A lot like sensors, but it actually helps the calculation along. So pretty easy to set up, right? It's shocking because this is solving the Navier-Stokes equations and doing some real complex stuff, but very easy to set up. I won't run it because it runs a little bit longer, but check out our YouTube channel if you want to see what the solver looks like. I've got a bunch of videos there, even a playlist on flow simulation, and we show you how to monitor the solve as it runs so you can make sure, oh, did I tell the air to go the wrong way, or is something getting cold and should be getting hot? No need to wait till your results are done to see that type of stuff. So let's get into some results. Let's look at them. First ones I always recommend are cut plots and surface plots. Even though it's tempting to go to those arrows they call flow trajectories, you'll never miss information in a cut plot. You can really find out what's going on. And here I can see the type of mixing we've got in our default configuration. Might look okay. I got a number of cut plots that show it. Well, it doesn't really go that far, and it looks like it kind of stays along the top here. Let's look at some of those flow trajectories and see if they show me any more. And I'd say, yeah, it looks like it does kind of swirl and stay along the top with my pipe, you know, in its default position, not going in or penetrating or anything. So if we just take a surface plot the outside, I can see, yeah, okay, it is, all the exhaust gases are over on one side. That's not a very even distribution of these, looking at mass fraction on that outlet surface. Another cool way to look at that would be point parameters in the tree. Kind of tell SOLIDWORKS, hey, put 20, 30 points on that face, and then give me the mass fraction of exhaust gas at every one of those points. It just spits it out to Excel. You can get fancy, you can calculate a standard deviation, and then you can really tell yourself by the numbers, hey, is that smooth and even at the outlet or not? Here's what all the goals look like when they get spit out to Excel. So this is all automatic just by going, hey, I want to know what's the max velocity globally. It shows you the absolute values, its progress through the solver. That's what these curves are as the solver iterated. For instance, the first one, I can see my average temperature started here at 40 degrees. About 60, 70 iterations in, it was a little over 110 degrees C, and it was nice and flat and smooth from then on out. So there was no more changing going on, and the software knew that it was done. Oh, so that's a lot more insight than you would have got. Yeah, definitely on a bench test. You can really get measurements in a way that are not even possible on the bench test. And then, of course, the visual supports to help people accept your idea. But the bigger thing here is investigating differences, looking at optimization, making the best thing. Not just, is it going to do what we need? Is it the best at doing what we need? Now here, I could optimize with a length. I could say, let's make this thing longer so that it goes down in. I want, my goal would be to achieve a certain mass fraction within a tolerance, and I'm going to let the software change the length of this pipe. And then I could let it iterate and solve over and over. Or I could just come up with 3 ideas, right? Maybe take the betting pool in the office. Somebody's got to buy beers today, whichever comes out, whoever's wrong on the testing. Someone says, let's turn this pipe. I have one extended in the middle of the stream, have one that's turned, so it's facing the stream, which makes sense to me. And then we'll see which one creates the smoothest. Literally same as I did in my very initial sim. Clone the study, right? So we've got our different geometry without having to set anything up again. Run it. Use the comparison feature to look at your results side by side. So that's what I've done here. You can even batch run these so that you don't have to run one and then the next. You can just, keep on cranking through. You could set them all to run. You could set this thing up to run, 100 studies and then email you when it's done. And this will use all the computer that you've got. A lot of times SOLIDWORKS is limited to just a few cores and we're all looking at CPU speed or can't make use of as much RAM as you want. This thing will use as much computer as you give it. And you can limit it. You can actually say, don't use all my CPUs so that you can still browse the web. All right, here's the first visual of our output surface plot here. The default one we know about. The extended, which looks actually really good. The turned one actually concentrated the exhaust gases still too much in kind of a central part there. So visually, I can already see the extended one is the way to go. If we go back to our standard deviation outputs from those point parameters, here that means smaller bars are better. I can have the math to back up that my extended design, despite not actually being what I guessed, I'd be stuck buying around a beer today, is the one to go with. And we've got the hard values to compare. Well, just how much better is it? So that's an easy way to do side-by-side stuff. I think fluid dynamics a lot of times seems unapproachable to folks, but to give you an example, when I teach folks how to do simulation in SOLIDWORKS, just static analysis, is it strong enough? The stuff that comes in SOLIDWORKS Premium. I spent 3 days doing that. It's pretty jam-packed 3 days. For flow simulation, 2, just 2. So it's actually less training because it's easier to use. All of the things we're doing, it's quite a bit more complex. And you can really go a lot further with here. I didn't get into the optimization suite here, but as you can imagine, we can really ask it to rerun these studies, and get us the best design, not just our best guess. All right, maybe it's another good time for me to look over at questions. Kaylee, we get any that come in?
We did, and I was just typing something, but since you're at a good stopping point, maybe you could talk about it. There was a question on if flow simulation can handle a high-speed flow, such as between Mach 0.3 and Mach 3.
Oh yeah, cool question. I love that question because the answer is yes. I like it when I can just give a hard yes on stuff. This software was originally made for rocket nozzle design and Mach flow. Like back before it had any interface that you could plug into SOLIDWORKS, that was its bread and butter. And I believe the software can go up to like Mach 7, but after you get over Mach 5 or 6, there might be some other physics involved, like particle ionization, weird stuff like this. If you get above Mach about 1.5, while you're solving, you're going to start to see messages that say, hey, you've got high Mach flow going on. And what you should probably do then is get back in the wizard, and there's a checkbox here for high Mach number flow. So if you start getting above, say 1.5 to 3, I saw that, see that's there in the question, then I would just check this box. It is going to slow down your solve. There's some other equations that need to run, but it is totally capable of it. Cool.
Yeah, and I did find, I knew there was a limit, so I was looking up in the knowledge base, and it does say you probably should not use it if you're going above Mach 5.
Oh man, I can't, yeah, I'm impressed with myself remembering that number. I don't see a lot of applications that get near that. Generally what I'll see is a Mach flow warning because we have created way too high of a pressure drop somewhere and the velocities are through the roof, and then we know, oh, okay, we should stop the solve and then go back and change our pressure drop or our velocities or mass flows.
All right, and then there's a couple more questions that came in. We'll do I think the easier one first, which is, can the solver do chemical reactions?
Yeah, unfortunately the answer is no on that one. It doesn't do. So we could do mixing of gases. In this case, if the gases reacted at all, it wouldn't be possible.
And then the other question that came in, it asks if FlowSim can do reacting flow with either a Chemkin or Cantera mechanism. Is that something that you've ever run into, Philip?
It's not. I'm wondering if, and maybe they can give us a little more information. Ask the question again with a little more detail in there. But I'm wondering if that reacting flow is chemical reaction, and maybe that's why I haven't heard of Chemkin or Cantera. But yeah, it's not something I'm familiar with. I'm going to go ahead and say no, that it can't. I think I would have heard about it. There are some interesting named effects that you run into in CFD, like the Coanda effect. So I'll hear these things and go, oh, and I'll do a research and find out, oh, it can do Coanda effect, cool. But yeah, it looks like that's right. They're reactions, so the software couldn't do it. I'll tell you the limits, yeah, are usually chemical reactions. Extremely low vacuums, let's say, because you actually want to do a gas flow, but you're near your near perfect vacuum like space. This uses a continuum flow assumption, so the particles get so separated that starts to break down. That's pretty rare. The other one is things that are dominated by surface tension is a limitation. So capillary action, atomizing into very small bubbles where the bubble shape is held up by surface tension, this won't do either. We've actually got ways to get really close to most of those things. For instance, there's a particle study in here. So if we had a line that air was getting into that we didn't want to get in there, is getting in forms of bubbles, we would first run the flow simulation, and then as a post-process, we would do a particle study and inject these little bubblets of air. They work as if they're round and we can track where they go, but it's not exactly fully simulated during the flow solve.
And there was one more question regarding explosive simulation. So we may have to break that down because I know we've used FlowSim for some aspects of like firearms.
Yeah, we sure have. I've done some exploding stuff with it. Actually, on our YouTube channel, you'll find fireworks that Marcus Brown has done. It's a very cool firework display. We've blown up a mailbox with it. There's firearms for sure, suppressors, you know, as a bullet goes off and gas expands. What I would think about that there is in flow simulation, our models themselves don't deform. So you can set up, you know, an explosion, basically a very high pressure event happening in a very short time span as an explosion. And that's going to map to things like the pressure distribution on things. But those things, those solid bodies themselves, they won't tear apart and explode. But you'll see all the explosive gases, and you'll see what the pressures and forces on those bodies were. Does that make sense? Am I making sense?
Well, it makes sense to me. I would say to the person who asked that, were you thinking of a specific application as far as an explosive? Just to make sure.
Yeah, and a lot of it comes down to, do you need to see damage on the parts and bodies? That's the part you wouldn't see, is damage on the actual things. If you tie it with SOLIDWORKS simulation, you could learn more, because you could say, oh, there's a whole lot of pressure on this thing. Now I can run that in a simulation, find out if it can survive that pressure.
Right. So that's kind of goes with some of the clarification we got about the explosion containment and failure point. So yeah, there is, like Philip said, there's actually settings that you can bring flow simulation results into actual FEA simulation and utilize it. So Philip, do you think that would be an application where you can actually utilize both?
I actually do think that would be a good application. What you could do is, for instance, let's think about the mailbox that I blew up. Inside of that, I can do a surface plot of pressure on the inside of the mailbox, where like we're kind of simulating a firecracker going off, and you can see where the highest pressures were visually. And then we can move into back to the regular simulation FEA world, and we can import that pressure distribution as our input, and then we can run a little study and see, okay, where was the maximum stresses and displacements in the mailbox itself. Yeah, I think that's a good application. That's pretty cool. That'd be a cool one. I mean, blowing stuff up is always cool. Good way to do a little non-destructive testing digitally. Yeah, sometimes when you run into these things that are limits and we're pushing the software as far as it can go, you know, an important job of me is figuring out, is this a good application for it or not? Not just in technically could it get there, but practically can it do it? Have I seen it done? What approach would you take? Because you can go above and beyond this, right? So what I'm talking about next, actually, next level simulation tools, because Dassault Systems is a real juggernaut in the software space. They own SOLIDWORKS and they own a bunch of other stuff. They own a brand of softwares they call Simulia, and that's where you'll see all their different sim stuff. So that's where, if you guys know the name Abaqus, that's been out there for a long time, is an extremely powerful nonlinear solver. They've had that for a long time. And now they're starting to connect these softwares together through their 3D Experience platform. But sometimes we'll find where we go, hey, we can't do chemical reaction in the SOLIDWORKS tool set. Can we find another tool from Dassault Systems that does chemical reaction? That way we could connect to it through 3D Experience, and we could still make design changes in SOLIDWORKS and see those design changes pushed to our simulations. So I think I'm going to roll into that. Keep the questions coming. We're going to roll back to this. Let's then talk about some next level simulation tools if we find out that maybe we are a little bit limited here. Bear with me. I'm going to get down to where we were just at. There we go. The next level, how to go above and beyond. You know, I actually already talked about some simulation tools that we're using now thanks to Dassault Systems owning a bunch of stuff like new meshers that are in the software. Or I talked about that topology optimization is part of just the technology share of, you know, the SOLIDWORKS Corporation being owned by Dassault. And so what we've had for, you know, as long as I've used SOLIDWORKS is these three solutions that fit for basically every designer and really every engineer, even if you got some complex nonlinear dynamic stuff. But there are places where the functionality runs out, and we haven't had anything above this. Like, you know, for large companies that have somebody who's a dedicated analyst, they might be in the world of Ansys and Nastran and COMSOL and whatever other, you know, fluid dynamics programs, and there'd be a disconnect. We'd save to a step file or whatever, send it over there, and we couldn't do these design updates and parametric optimizations. But now we have that ability in the last 2 years through the 3D Experience platform. There's 2 licenses, actually a couple licenses that connect right into SOLIDWORKS. The ones I'm going to talk about today are specifically for FEA, but there's kind of a lot of tool sets. The first one is called Structural Performance Engineer. It's the name of the license, and it is a nonlinear solver. It is the Abaqus nonlinear solver, but you don't have to go back to the old interface of legacy Abaqus. You get this nice new interface that's connected to SOLIDWORKS. And above that, we have one called Structural Mechanics Engineer, which is the implicit and explicit dynamic solver of Abaqus. Now, there's some other tool sets here too. They have some plastics and some flow. They don't really give us much more physical capabilities than we have in SOLIDWORKS, maybe some cloud benefits in solving, but there is a really nice electromagnetics one called Studio Suite or CST Studio Suite. And that's a really powerful thing that we don't have inside of SOLIDWORKS. So kind of sky's the limit as long as we can connect SOLIDWORKS to it. Now on the FEA side, a couple things that really stand out to me as soon as I started getting my hands on the software, I'm going to put up front. The first one is contact. You know, when we're in SOLIDWORKS, how does one part connect to another? The default is that they're welded together if they're touching, or we'll go around and change a lot. The default over here in the 3D experience is that everything has sliding complex contact. You don't have to change that at all. I mean, you can, because you can do a lot more here. Your controls are much more in depth, but that is actually the default contact. Also, the meshing gets quite a lot cooler over here. We are not stuck with tetrahedral elements anymore. This is where you can get to hexahedral elements, brick meshing, continuum shell elements. It's all of the meshing that comes with Abaqus, but in a nicer, easier to use interface that connects to SOLIDWORKS. So contact and meshing stuck out to me a big deal. Of course, over here, I'm generally doing much more nonlinear simulations than I am in SOLIDWORKS, things that are well beyond their yield point, or dealing with rubbers, you know, hydroforming, packaging designs, blow molding, or getting into structural mechanics engineers, things that are heavily dynamic. You know, Abaqus is the kind of tool that BMW uses to simulate car crashes digitally, and that's the type of solver. I mean, that is the solver we're talking about here. So we get into a much bigger world. So what I want to show you today is a company called Resman that makes heavy equipment, and the way that they switched to this. They've been a SOLIDWORKS user for a long time, and really they've done a pretty impressive job of growing into these SOLIDWORKS tool sets with SOLIDWORKS PDM to manage their data. And a lot of folks come to 3D Experience for easy data management. It's basically the OneDrive or the SharePoint that is purpose-built for SOLIDWORKS and understands file references. But in this case, you know, they came here specifically for the simulation tools. And that's what we're going to look at right now, is the design tools of SOLIDWORKS and how they could be connected to these higher level simulation tools of Simulia. So this Resman company, they're actually down in Peru. They make a pretty high volume of these heavy equipment drills for mining and tunneling applications. They've used SOLIDWORKS simulation for a long time, and their main interest in getting into another level of simulation here was to reduce warranty claims. And that really came from fatigue analysis. There'd be, you know, a certain percentage of fatigue failures, and you can imagine drilling, it's pretty rough, and tunneling, and they want to reduce that amount. So the first step is simply to connect SOLIDWORKS to 3D Experience so that you can then save your models into 3D Experience, open them up in the sim apps, and work with them. So this is all done through a web interface. It's almost like a web interface that's a remote desktop connection. You log into it, you've got a start button in the top left, you find the tool you want to work with. In this case, it's called Design with SOLIDWORKS, and it actually launches SOLIDWORKS on your computer. You can just set it as your desktop SOLIDWORKS add-in too, or just load the add-in. I usually access it through the web browser right there, because then I know it makes a good connection with the database, and then just open up the files you're working with. Now in this case, we'll be leaving the world of Windows Explorer and saving our files into a cloud database. That's the 3D Experience data management. This all happens just on the right side of my SOLIDWORKS window in this 3D Experience task pane that's popped out. Now, as we save this up, it's going to translate the data really into a different file type that we never have to worry about. And this takes care automatically in the background of the settings set this way. So when I save this up, it's going to put them in the cloud, and all the processing of translating the files into that other file type is done on the cloud. You never have to worry about it, and it never really disconnects anything. You get all of the information you'd expect from a data management tool in the task pane. Like, have the files been saved up? Have they been converted so that all the other Dassault System software can work with them again? On the 3D Experience side, we simply need to search up that assembly. It's a pretty instant search because you're in a database. You could also drop them in your working folders or your live searches, but just go find your file and then open it up with the simulation tool you want to work with. It's interesting because the simulation tool and SOLIDWORKS are both installed locally on your computer, but now we can do some more interesting things. We can access the data from anywhere through its cloud databasing, and we can do some cloud solving and meshing as well, which I'll get to. So there's the cloud benefits you'd expect, but I don't want you to think that this is a 100% cloud software. It's cloud enabled software. We're still housing things locally, and if you disconnect from the internet, you know, you still got your SOLIDWORKS files down there locally. So that's it. I mean, you can see why it's pretty easy on data management. That's it for that data management side. Let's get into now the heavier program under the Simulia brand, this one being that structural mechanics and durability for fatigue. Now, this FEA has a 3-step process, maybe slightly different from what you're used to in SOLIDWORKS. So first, we're going to build a finite element model, or FEMREP. That's going to include our materials, our meshes, and our connections. And of course, it's all linked to the actual SOLIDWORKS geometry. Then we're going to get into a scenario where you create the steps that you would normally think of as a study. There's going to be explicit dynamic steps eventually. We'll start off with a simple static nonlinear study. And that's where you put your loads, you know, your fixtures, what kind of outputs you want. And then the third step is just jumping into the results and seeing how the numbers come out. Let's share this with other folks. What tools are we going to use for that? So while the finite element representation, or the FEMREP, is not something we usually use in SOLIDWORKS, the steps are pretty similar here, and there's an assistant panel that can walk you through it, so similar to the study advisor you find in SOLIDWORKS. Now we are going to use a different material library over on the Simulia side, and this library is much more extensive than what you're going to find inside of SOLIDWORKS. For instance, on the fatigue side, you're going to be able to get SN curves a lot easier here. And notice the interface does have a tree structure on the left. So as far as finding the materials and then, you know, applying to the tree, it should be, you know, pretty similar process. Of course, the meshing capabilities is a huge reason to come here as well. So when we look at the types of meshes available in Simulia, there are a lot of formulations to deal with. In this case, when you look at the geometry, we've got really similar looking parts. There's not something that's suddenly thin or something that's, you know, it's all kind of plates and square tube. So what we can do is create a mesh rule and say, okay, for most of our geometry, we want to use these similar types of settings for meshing part by part. And then using the tree again, we'll just apply that rule to the different parts that we want to use it on. So in this case, I'm going to search up that rule that we just created, and I'm going to apply it actually to every body in this case. I don't think there's even anything in here that this wouldn't work for. So by one click, we can apply it to all. And you'll see the same thing for when you mesh. There's one click on an update button, and you can watch this mesh generate from part to part. Generally, I use my local resources for meshing. It happens very fast, and usually it's faster than even on the SOLIDWORKS side. And because this goes part by part, and you've got the local control too, if something fails to mesh, you'll notice on this one part, it's not going to fail over the entire assembly. You know what, just to drive the point home, if you're back over in SOLIDWORKS and you change something, such as the angle mate of the design, that is going to update automatically in 3D Experience. You hit the update button, anything that's new is going to be there. So we're in a different interface, but we are completely connected. That's what the corporate guys call a single source of truth. But it means we can do the things that we expect as a SOLIDWORKS user. So still in the FEMREP, I want to create some connections here for parts that are not here, just as you would in any FEA. I don't want to actually simulate all the bolted connections when I could just use a bolt connector in their place and save a lot of solve time. And what you're going to find is all the connectors you would expect are here and more, but their panels have some more inputs that you could put things in that you wouldn't even have in SOLIDWORKS. So they are a little bit more capable in simulating the real world. Now, as I replicate these to the other bolt holes, notice that I'm not looking for a feature in a SOLIDWORKS tree. It found these other bolts just by looking at the geometry and going, that looks like a bolt hole. It didn't rely on any history of the files themselves. And you actually could just start this from a step file, if you really wanted to. Now on our project here, just like bolts, there's actually some linear actuators that raise this thing up and down. And I didn't want to simulate those and mesh those and solve those. There's actually a really cool link connector in SOLIDWORKS Simulation 2022, and I'm mimicking the same type of deal here. So it's another great way to simplify the geometry for simulation without compromising on the real world physics. You can even include the damping information here for more realistic behavior, just like you can, get into more realistic behaviors for these materials. And then this process, in my case, I actually did twice, once for each side of that boom arm. All right, finally, you might remember the remote loading that I put in my initial FEA today when I did the topology optimization. I want to do a remote loading here as well. I don't want to model every part, so I'm going to create a coupling in the FEMREP. This couples a point in space to the end face of the boom. So later, when I'm in the scenario, I can apply a remote load right to that point, and that's going to be equivalent to the weight of like the machine equipment that's supported by that face, the stuff I'm not really worried about, but I need to include its effect. Now, all sorts of other connections can be made or created. So there are managers, kind of like features managers. Here's the connection manager so you can review all of them. And in fact, a historical manager exists for every step along the way. So if you're not using the advisor to go step by step, you can see all of that in a nice feature manager that I'm more used to inside of SOLIDWORKS. So you just see how to save designs from SOLIDWORKS into 3D Experience and prepare them for simulation by creating a FEMREP or finite element model representation, and that includes our materials, our mesh, and different connections. Now it's time to delve into the actual scenario, the simulation setup, where we're going to define the steps for the real world conditions, our real world boundary conditions, our fixtures, and our loads. Luckily, the user interface doesn't really change much. You just choose the different model scenario creation app, the different program from that compass dropdown, and the tools of that app are now loaded up. So it's not like you went to a different app and opened a file in it. You just switched apps and kept working. We need to pick the finite element model, and so I'm just picking the one that we just created, and then you're ready to go with the scenario. Now this is going to start with a nonlinear static step. So really, I'm just going to review the step size and the solver settings for that. We could run the default here. Ultimately, I'm going to make it a little easier. I'm going to take an initial larger step, and I'm going to want to end up in an explicit dynamic and, of course, get fatigue outputs too. Now, you probably noticed earlier that I defined some connections, but I didn't define how each component was contacting its neighbor. And I mentioned by default, this is going to be sliding, what they call no penetration or contact. But I can make that even more realistic by creating a contact property. So I can include stuff like friction or whatever more, real world functionality I want. And then I can use a contact detection tool to just look over the whole model and find all the face pairs that are within, in this case, 1/10 of a millimeter, and then apply that contact property to all of them, or tie them all together if they're welded. Now, of course, we need to define the connection to the real world, right? The rest of the stuff that's not here, and that's just like fixtures in SOLIDWORKS. I'm just going to restrain this back face for displacement in the X direction, and that should be enough to hold everything down so we don't get rigid body motion or things flying away. All right, looks good. The loading is a remote force, and I'm applying it to the point in space, that coupling that I made earlier, and it needs to support 2,200 pounds in the negative Y direction. And since we got more than one load case, I'm going to duplicate this. Just like a copy study, there's an actual button for duplicating the case, so I know I've got an exactly identical setup and connections and FemRep and all that good stuff. And I just want to modify the loading so I could have a different direction of this load as well. Okay, all that looks good. So finally, I want to see the effect of both of those loading scenarios, both duplicated carriers, in a fatigue study. And this is a fatigue life called a durability case, which handles both low and high cycle fatigue. And technically over in simulation, we only do high cycle fatigue. Mathematically, that is very different. Your lowest number in SOLIDWORKS simulation of cycles ought to be 1,000. Really, maybe 10,000, but 1,000 is the lowest you can go. Here we can do high stress, low cycle fatigue. And in this case, we're just setting up zero-based loading for these cases. Now, before running the simulation, once you've set all that stuff up, you can run some model and scenario checks to really make sure you've got everything. Maybe you forgot a fixture and the thing is going to fly away. Catch those mistakes before sacrificing solve time, and doing some kind of trial and error approach to figure it out. You can run scenario checks, especially if you're spending a little money here with credits or tokens to solve on the cloud. You can use Dassault's cloud solving here and get up to 144 CPU cores. It does cost a few credits or tokens to do that. Or you can solve as much as you want locally for 8 cores. There's no limits to how many times you can run those. Okay, so I define my boundary conditions and setups for the analysis case in the scenario, enough to produce multiple load cases there and produce some fatigue results. There are some built-in results that are going to come out, just like in SOLIDWORKS when I saw stress, displacement, factor, safety, and then I can ask for more results or go around and probe and see what we've learned. So the main KPIs that I want to review here is going to be von Mises stress, max stress in here. So let's probe and set up a flag for what the max is. Here I can see it over my time, my iterations of the nonlinear solver, pseudo time, so just going 0 to 1 second. You can see, okay, this basically linearly increases to the maximum, and the max point is actually where I expect it would be. Okay, that one looks pretty good. We might also look at displacement and note, yeah, where's the max of displacement at? I would expect it to be out here closest to the load. I think that makes sense, just as I would in SOLIDWORKS. So how about fatigue? Here we're looking at log of life in fatigue. It's about 5.86 for the max or minimum here, which is not good. We actually need that to be higher. So let's do sensors just like you would in the SOLIDWORKS simulation once again, and we can make some design changes and our sensors will tell us right away, are we heading in the right direction and have we done enough to meet our goals? This also makes it easier to really share this information with other folks. And I can see right away if I set some limits on those sensors that we're not there yet. We're actually failing in both situations. Clearly the fatigue is not over 7. That's not going to be enough, and the stress requirements aren't there either. So of course we move into the design change cycle. Right? How was this designed? It's back over in SOLIDWORKS. It's probably a weldment, but basically we got a piece of square tube here we're thinking about making thicker. This might not be the same person who's an analyst, right? This software, this high-level sim software, Abaqus stuff, could be run by somebody who's just doing analysis problems all the time, and your design engineer is handing stuff off to this person. In that kind of situation, it might not be easy to just switch back over SOLIDWORKS and make the change, right? You got to actually just, shoot a note over, use one of the communication tools and tell the engineer, hey, I think this thing needs to be thicker. It's failing. But then the question would be, how thick does it need to be? All right, we don't know. We're going to iterate and go back and forth? Of course not. I bet you guys can imagine already. We're going to optimize and have the software figure this out for us. So the first step is for the designer to go back to SOLIDWORKS, actually open up the part that we've identified that needs to be thicker and make the change. This is pretty easy for them because it's a cloud data management system, right? So that maybe they're at home, they go grab it, they open it up, and they're adding parameters the same way that we would do in Simulation Professional to run an optimization study. I ask, why are we doing that? We're going to give the analyst control of those actual key dimensions and parameters. So that was it. We actually didn't make a design change. We just set up parameters, same as you would if you just were doing everything in simulation. Now we just need to check out the files or lock and unlock is the name in here, but for you PDM guys, check it out and save it. That's it. That's going to push whatever changes we've made, in this case just a few parameters, over to the analyst or the world of simulation. Now maybe you're the same person, it doesn't really matter. When you get into the tree structure over inside of simulation tools, you'll find you can't change the SOLIDWORKS features, not available to you. The only program that can change a SOLIDWORKS feature is SOLIDWORKS, just like everything else. But through this parametric bridge functionality, we can bring in the parameters that the designer is allowing us to change. So here they are in the tree, I can see what they are now, and I can change them. That means as the analyst, I can decide exactly how thick I want to try things out with, or I can get into those optimization tools and link those and let the software figure out exactly how thick they need to be to get above our failure criteria, our sensors, and still be the least amount of material and the lightest that they can be. So at this point, there's nothing left to do but rerun the simulations. With a newly edited design, and check the key results using the sensors we created before. So the sim results now ought to look good. They ought to meet the KPIs, and they really ought to show up in green now and not give us any warnings. Side-by-side comparison, just like you can do inside of SOLIDWORKS, is available, and there's some really nice output tools here as well if you have other users on the 3D Experience platform, or if you just want to export out, you know, PDFs or AVIs of these images. So we'll set up comparisons the same way, and then we can show others, hey, this is what the size needs to be. You can really tell when you're looking at the A-B comparison. Great, I think that looks good. I'm hoping people will now say, you've done it, you've passed, you're a genius, you'll accept the design. And this is a real case study that happened at Resumen. This is how they use the tools to figure out, can they not just survive the load, but can they use the least amount of material to survive it and then get a better fatigue lifespan response out of it. So there's a few steps to it. The handshake between SOLIDWORKS and really any 3D Experience program, connect them together, save your data into it. The analyst is going to set things up with a finite element rep for materials, meshing, and different model connections that they want to use. Then they'll create a scenario that actually has the inputs of loading and fixtures, and finally review those results, whether we're going to leverage updates back and forth or just share those results with others on the team. So from a technical perspective, that means using simulation as a design tool even here, just as we always did with SOLIDWORKS, but now with way more power and ultimately leading to better quality designs. We're taking advantage of cloud computing and storage and data management, which simply increases the overall efficiency of the entire process. So from a business side, you know, that's a connected set of tools to increase team collaboration and communication, and just leads to more innovative products when you have that built in. Not only is the overall engineering cycle time reduced, but IT overhead and infrastructure costs pretty much go to zero. Right? You don't have to set up these servers and update them yourself. For Resumen, these advanced sim capabilities, they led to reduced warranty costs and recalls due to better fatigue performance, which ultimately enhances the brand value overall, you know, not just the bottom line revenue. So if you're worried about the licensing, what you saw here today is in the durability and mechanics engineer role. There's a performance role, which is nonlinear, a mechanics role, which is dynamics, and the durability and mechanics, or durability and performance. That durability word means fatigue. It's the licensing for it. No matter what you're doing, even if you're just getting an X shape because you want to do push-pull, sub-D type modeling, and then pull those files into SOLIDWORKS, you're going to see that there's a collaborative business innovator, which gets anyone logged in so they can, you know, see results and communicate. an collaborative industry innovator role, which does all your data management stuff, and then a collaborative designer for SolidWorks, which connects that together. Awesome. So I hope that gives you kind of a taste of what can be done with 3D Experience. It's just in their FEA tools, but check it out on YouTube if you're interested in connecting to more of that stuff, because sky's the limit over there. It doesn't have to just be simulation. It could just be data management. It could be designing with web apps that run 100% in the cloud and don't require any local install. We've got a lot of content, especially me and Kaylee, that I've made for our YouTube channel on that. Speaking of which, Kaylee, did I get any more questions come in? Oh, cool.
So the first question was, what like specific computer components should be considered for like an upgrade or baseline performance when considering simulation? And the idea here is to reduce simulation time or lag.
Mm-hmm. Yeah, that is a good question. It's a little dependent on which simulation tool you're running. If I start with the first one I ran today, like SolidWorks Simulation FEA, RAM and CPU speeds are up there. I usually find if I devote more than 8 cores to SolidWorks Simulation, that's where I start to get a lot of diminishing returns. But I'm also doing other stuff on my computer at the same time the sim is running. So, you know, I'd usually say buy more CPU speed and less cores. You know, if you go out and buy 32 cores and you're just running SolidWorks FEA, you're going to have diminishing returns on that for sure. After about 8, I think it falls off. RAM for sure, just buy it. 32 gigs, I think you'll be in a pretty happy spot. I see machines with 64 a lot now. It's just cheaper. Now, if you get into CFD, the SolidWorks Flow Simulation, then the multi-core does help more. I don't see any drop-off there, and the RAM will help you a lot there too. The GPU won't help you in that case, but it's SolidWorks. You could always use a nice GPU. And then the cloud stuff as well. For any of this cloud-connected stuff, so I'm talking about tools that don't run 100% in the cloud, but SolidWorks connected to it, or these simulation tools. For those, you actually can, you can always run 8 cores locally for free, and you can actually spend those credits to unlock more of your local cores. So instead of unlocking the cloud cores up to 144, you could spend them to unlock your local stuff. So if you already have some crazy, you know, workhorse machine, you can use it for that. Yeah, I just should say the biggest thing, the number one thing for simulation speeds is in the setup. It's in the meshing, the contacts that are used, any simplification you can. So that's, you know, a big point of our training curriculum, like I mentioned earlier with meshing, is efficient solve times. Yeah, there's a few companies out there that make computers specifically for simulation purposes and SolidWorks purposes. I don't want to plug any of them. There's a few of them that I've used. I really have not been unhappy with any of them. There's a really nice one based out of Austin, Texas here. And sometimes I'll look at their machines and go, okay, this is the one that they're speccing for a SolidWorks simulation high-end machine. And I'll just note, you know, what they're putting together and then see, well, can I put something else together on my own that, you know, gets me close.
All right, well, sounds good. I'm glad that correlated with how I replied to that customer. It also kind of brings up kind of an interesting question too, which was when you and I first started getting into like the 3D Experience software, we do actually find that for like the nonlinear, it ends up reducing a lot of meshing and run times for those higher end nonlinear studies, which I think is kind of worth throwing out there as well.
Yeah, that's the first place I see people jump on the sim side. The first place I see them going to 3D Experience sim tools. A lot of times you'll set up a more complex study in SolidWorks nonlinear, and maybe it doesn't solve all the way through. Maybe it only solves like 80%. And that can certainly happen like if you have, let's say, really high strains. Like for instance, you can't inflate like a balloon in SolidWorks in simulation. You'll find some point where those elements that have meshed the balloon are stretching too much, and the software will just run out of what it can do. But you could take that same thing up to 3D Experience, and you could do it with the nonlinear, with the Abaqus meshers and solvers that are over there. So I think that's pretty cool. But yeah, just apples to apples. If you just take a nonlinear study you're running in SOLIDWORKS and then you run it in 3D Experience, it's actually going to be faster.
All right, and then also I just put this into the chat, not through a specific question, but when that question came up, I did actually find a video through the My SolidWorks website. It's for free guest access, so everybody has access to it, but it's from SolidWorks World, and it's specifically about tuning your simulation study and hardware. So that's something that is in the chat. You guys can click on it. And then there was one more question, and again, this goes back to the chemical reactions and just confirming that, at least through the Simulia products on the 3D Experience platform, that it does not handle those chemical reactions. Is that?
That's true. Yeah, I haven't seen that yet. There are some other products that Dassault Systems owns that do it, and kind of over time, I think you might see those get built into their 3D Experience platform. They don't do it yet, and the flow, because we were talking about flow with chemical reactions, the flow programs that you see on 3D Experience, they don't have any additional physical capabilities over what you have inside of SOLIDWORKS Flow Simulation. They offer some benefits in meshing, in their solving capabilities, and in their turbulence models, but there's no new physics over there, like chemical reactions.
All right, that's what I thought. I figured we would just verify that information. I do know that there's some other brands on the 3D Experience platform. So just for everybody, the 3D Experience platform as a platform is very, very deep. And there's only a kind of like a sub-compartment that we at MLC work with and sell. So for the person who asked that question, we can always see if maybe there's a different brand that currently does chemical reactions, because I believe there is, but it's not one that we typically work with, so we'd have to just figure some things out there and make sure it would be able to do that.
Yeah, it's worth asking. I mean, for us, the solutions that we put out for everyone are things that are all connected together. You know, and that's how it's always been in SOLIDWORKS, from the days of going from a 2D DWG to SOLIDWORKS, where you got part drawing and assembly and all your files understand each other. And now as we go into, you know, higher level sim or any other 3D Experience tool, you know, we don't really get into anything that would cause some complete disconnect, though that doesn't mean we don't have it. We just kind of don't put it out there as a #1 solution. For instance, maybe you want to use Abaqus, but you are doing defense contracting and you can't save anything into the cloud. No problem. We do have legacy Abaqus, the old school one. So we have tools like this. You know, talk to us about it, you know, afterwards, if that kind of stuff is something you're looking for. The tool set is extremely deep. And of course, me and Kaylee work a lot on it, and Mandy will be happy to send you any information on what tools are available too.